Welcome back to The Explainer. Today, we're diving straight into a fascinating piece of microscopic traffic control that is literally happening millions of times a second right inside your computer's CPU. We're talking about victim cache strategies. Now, to make sense of this invisible world, it helps to imagine your CPU's memory as a physical workspace. Your main memory? Well, that's like a massive distant filing cabinet holding absolutely everything you could ever need. The CPU's immediate memory, though, the L1 cache, that's your actual desk space. Naturally, space on the desk is highly limited, but whatever you put there is incredibly fast to access. This explainer is all about what happens when that desk space gets, well, completely mismanaged, and the brilliant engineering that was designed to fix it.
Here's our roadmap for today. We're going to start with the cache memory problem. Then, meet the victim cache. After that, we'll look at how victim caching works. And we'll wrap things up with the selective victim upgrade.
All right, part one, the cache memory problem.
So, to really understand why a victim cache is even necessary, we've got to look at the extremes of how a processor organizes its desk. On one hand, you have a direct mapped cache. It's incredibly simple, super cheap to implement, but its fatal flaw is extreme rigidity. There's a fixed, predetermined spot on the desk for any given block of data. No exceptions. On the completely opposite end, you have fully associative mapping. This one is highly flexible and absolutely maximizes your hit ratio because data can literally go anywhere on the desk. But the downside, you need massive, highly complex circuitry just to constantly check all those cache lines in parallel to actually find your stuff. We desperately needed a hybrid approach, right? Something that gives us the cheap speed of direct mapping, but without that crippling rigidity.
Because when that rigidity goes wrong, it goes spectacularly wrong. It leads to something called thrashing. Imagine you've got two absolutely crucial documents, but your direct mapped system stubbornly dictates they have to occupy the exact same square inch on your desk. So every time your program needs the first document, it violently kicks the second one off the desk all the way back to the filing cabinet. But literally a microsecond later, the program needs the second document again. So it fetches it back, booting the first one out, over and over and over. They are endlessly swapping, your hit ratio plummets, and your processor is just doing a ton of busy work fetching data instead of actually computing anything. It's a microscopic disaster.
Which brings us to part two, meet the victim cache.
This brilliantly simple solution to the thrashing problem was first proposed by Norman Joppy back in 1990. Now, what's really interesting about this architecture is exactly where this invention sits. The victim cache is actually part of the overall L1 cache system, positioned right between your rigid main desk and the lower levels of memory. Think of it like a tiny, fully associative, to-be-finaled tray that's just bolted right onto the edge of your CPU's desk. It's a small, clever safety net. It gives us the fast hit time of direct mapping, but completely catches that chaotic thrashing. And it is wild how effective such a tiny change can be. Joppy actually found that a victim cache consisting of just 4 lines of data, literally just space for 4 documents in our little tray, removed an astonishing 20 to 95% of misses in the direct mapped cache. Just 4 lines. By simply catching those data blocks that got casually discarded during a thrashing fit, this tiny buffer dramatically stabilized the entire system.
So, moving on to part three, how victim caching works.
Okay, so how exactly does a buffer this small pull off such massive performance gains? Well, if we map out the operational movement paths, we find a golden rule for this setup. The exact same line of data is never ever present in both the direct mapped main desk and the victim tray at the same time. There are 2 distinct cases for how data flows through this system.
Let's break down case 1. This happens when the processor looks for some data and completely misses in both the main L1 desk and the victim tray. First, the required block is fetched all the way from the main memory cabinet and slammed onto the L1 desk. But because that desk is direct mapped, whatever old block of data was sitting in that specific spot gets pushed out. That replaced block, the victim in this scenario, gets shoved straight into the victim cache. Now, because the victim cache is so small, if the tray's already full, it operates like a circular buffer. The item that's been sitting in there the absolute longest, that gets dumped entirely to make room for our newly evicted victim.
Now, case 2. This is the magic moment where thrashing is actually defeated. The processor looks for a document, misses on the main desk, but boom, gets a hit in the victim cache. That document is immediately rescued from the to-be-filed tray and promoted right back to the prime real estate of the main desk. And simultaneously, whatever block was taking up that spot on the desk gets swapped out and dumped into the victim cache. It's a completely elegant, direct trade.
I also really want to point out a super neat side effect of this setup. The victim cache manages its few lines using a strict FIFO, first in, first out discipline. But think about it. Because any reference to a block in the tray immediately pulls it out and rescues it, the blocks that actually stay stuck in the tray are the ones being totally ignored. So by default, this simple first-in, first-out queue actually naturally achieves true least recently used, or LRU, behavior. The block that eventually gets booted back to main memory will absolutely always be the oldest, most ignored piece of data in the pile.
Finally, Part 4, the selective victim upgrade. So JUPI's original victim cache was brilliant, but you know how it is in computer science. We never stop optimizing. In 1994, engineers proposed a massive step up known as the selective victim cache. Instead of just blindly routing every single eviction into the tray, this upgraded system uses a predictive scheme called the dynamic exclusion algorithm. It's basically a tiny crystal ball. It evaluates the past history of data use to actually predict the probability of future references. With this new intelligence, it selectively decides where incoming memory blocks should go and selectively decides when to perform those swaps we just talked about.
Let's compare how incoming blocks are handled now. In the standard 1990 scheme, a new block from the filing cabinet is always loaded onto the L1 desk, automatically creating a victim out of whatever was there. But with a selective victim cache, the algorithm steps in. It looks at the incoming block, looks at the block currently sitting on the desk, and asks, okay, which of you two am I actually going to need next? If the new line has a higher probability, it takes the desk, and the old line goes to the tray. But, and here's the kicker, if the algorithm predicts the current desk occupant is actually more valuable, it sends the incoming line straight to the victim cache instead.
And this same predictive intelligence totally changes how swaps work. Remember that elegant automatic trade in case 2? Well, in the selective system, it's not automatic anymore. If you get a hit in the victim cache, the dynamic exclusion algorithm fires up again. It compares our rescued victim block against the conflicting block on the main desk. A swap only happens if the algorithm decides the victim block is genuinely more likely to be used again than the current occupant. If not, no swap. This guarantees that only the absolute most valuable data holds the prime real estate on your desk.
And honestly, that's the true brilliance of victim cache strategies. We evolved from rigid, chaotic thrashing to a basic associative safety net, all the way to a highly intelligent, predictive data router. And this is all happening within the microscopic space of a processor's memory hierarchy. It leaves us with a pretty fascinating question to chew on. If a simple dynamic algorithm based on past history can predict what data a processor needs next this effectively at the micro level, how else might predictive memory architectures completely reshape the broader future of computing? Something to think about. Thank you so much for joining me on The Explainer today, and keep learning.